Christian, please, the stage is yours.
Thanks. Thanks, Jensia, and thanks to the organizers for inviting me. So I decided to talk a little bit about stochastic PDEs, so diffusive systems that in some sense have two diffusive components, one that comes from the PDE and one that comes from the stochastic terms. And I will only focus on sort of the main sort of ideas about bifurcations that we have developed. And there are some technical details of the stochastic analysis that I think for this audience, I will just skip over. But if you are interested there, of course, in all the references that are given in the papers later on. So what's the plan for today? So here's the plan on the slide. So first I will go a little bit over background and motivating examples and a few remarks on solution theory. Also, I added these yesterday after yesterday's talks. I've noticed that many people were interested in quasi-linear problems. And I wanted to do a little bit of a word of warning on quasi-linear problems. And then the second part will be results, two parts of results, one on analytical results on bifurcation type phenomena and SPDs, and one on numerical results. And I thought I would put the open question right at the beginning that the organizers asked me to have it here. The question is actually a big community program. The community program is really that we know a lot about PDEs and about dynamical systems theory for PDEs already and about pattern formation. And yesterday we have seen a very nice sample of that. But we know very little about the sort of same topics that you have seen yesterday in case there are actually additional stochastic fluctuations that naturally you have to take into account in many cases in modeling. So this is really a broad challenge for all of us, I think. And if you wanted to get yourself into sort of dynamical systems theory for PDEs, there are two little reviews. One is a little bit more theoretical, and one is a little bit more sort of directly focused on traveling waves. And I thought maybe that's for people who have never worked with stochastic PDEs, a way to get their feet wet. All right, so let's get started. So what am I interested in? I'm interested in spatial stochastic systems on a domain with an unknown u, and there's a stochastic process in space and time that I will denote by xi here. And then there are some motivating examples that motivated me to get into the theory. First is sort of the one that you can have in mind for the talk today. That's called sort of the Allen-Kahn equation, or the Wheel-Ginsburg-Landau equation, or the 5,4-D model, or the Schlögl model, or the Nagumo equation, depending on what community you are. It's basically reaction diffusion PDE with a cubic or sometimes cubic quintic nonlinearity. And you might wonder what happens to such systems if you force them by a space-time stochastic process. So the first one is really the thing you should have keep in mind for the rest of the talk. But the other interesting ones that got me interested, like FKPP, it's sort of similar to the Allen-Kahn, so this is really of the same class. But there are more complicated ones like SKT, which is actually this quasi-linear sort of SPDE, where you have to be careful with the noise and the terms that appear in the highest order differential operator. And also Fitch-Nagumo is a good motivation with noise. Yeah, all these are sort of examples where the noise is needed in the modeling simply because you're neglecting effects, you are neglecting forcings, you're neglecting all sorts of stuff that's in the model. And noise is a very nice way to capture all of this. All right, so a little bit of the definition. What is this xi? I thought I will at least try to give the definition for those of you who are not familiar with this. So suppose you take a Hilbert space and take an operator Q on that Hilbert space. For simplicity, I will take this linear, symmetric, non-negative. And let's denote the eigenfunctions by qk, the eigenvalues by rho k. Suppose this is an orthonormal basis, and a Q-Wiener process that's constructed from this Q is nothing else but this series here, where you take the eigenvalues, the spatial eigenfunctions, and you multiply this by independent, identically distributed Brownian motions. This is basically a space-time stochastic process where the spatial correlation structure is effectively given by this operator Q, because Q determines how this process behaves spatially. Yeah? This definition is quite simple. It's sort of a generalization of normal Brownian motion in finite dimensions to a natural spatial setting. So there are some technical sort of small scale script size remarks. Yes, you can prove that this converges in certain topologies, for example, in L2 into the continuous functions. The interpretation, as I have said, after you play with it a little bit, is that basically the Q determines the spatial covariance, so how points are correlated in space. And it's actually, unfortunately, and this is the difficult part technically, a very irregular process. For example, it can have sort of negative regularity in the sense that this xi that you define as the time derivative of W like typically you would in physics. Like this is sort of the typical construction of taking a Brownian motion and constructing white noise. This psi can have very ugly regularity that it's only in general a distribution, so a generalized stochastic process which has very low regularity. I will you will not see this directly in the statements of the results, but in the proofs you have to take care of the fact that the forcing is very irregular. Okay. Very good. So here are benchmark examples. This is the class I want to look at most. These are the sort of semi-linear SPDEs with additive noise. So meaning that the noise is just, there's no sort of U dependence in front of the noise. There's just a sigma that controls the size of the noise. The right-hand side would be the physics notation for this equation. The left-hand side would be the mathematics notation for that equation. And the question is, what's even a solution concept? How would you write a solution to this equation? You could try all these different concepts, but let me immediately say strong solutions are bad because you rarely have that U has two spatial derivatives. So writing a strong solution tends to be difficult. Today, I will purely focus on these mild solutions where you have a normal mild solution formulation where effectively you can think that this W or this psi can be viewed as you're just doing the usual Duhamel formula, except the fact that you have to reinterpret this last integral as a suitable stochastic integral. Okay? So you normally do the normal mild solution you are used to from deterministic PDEs, except one integral is more complicated to define. Otherwise, it's the same formula. Yeah? Take the semigroup, convolve it effectively with the nonlinearity. Here's the linear part, and you have this stochastic part that's also called the stochastic convolution that we will see later on that's a key object. There are other types of solutions you could do. You could do weak solutions, or like the sort of famous stuff of Martin Heyer when the noise is really bad. You could also do renormalized solutions. Now, I'm not going to talk about them today, but you should be aware that there are different solution concepts. Today, focus on mild solutions, variation of constants for formula, or for all the people in France, Duhamel formula, right? So, so a word of warning, this I inserted yesterday because I've seen many people who are interested in quasi-linear problems, like cross-diffusion problems, degenerate diffusion problems. We had several talks on this yesterday. And I just wanted to make sort of sure that there you have to be a little bit more careful, actually, because if U is stochastic, then A of U becomes sort of a stochastic object. And then it's actually difficult to define this mild solution formula by standard deterministic PDE methods, like you would, for example, in SKT or other sort of quasi-linear problems. You wanted to write this formula, but unfortunately, this formula for this evolution family E, which is the normal deterministic PDE formula to solve this equation without the noise, this formula, unfortunately, is wrong. So this formula doesn't work because you don't have the correct measurability properties of this evolution family for the stochastic integral. So there is a very sort of delicate issue of measurability that arises from the fact that you have the differential operator that becomes random. Just a word of warning, it can be fixed though. You can fix that, you can redevelop the concept of mild solution by a concept that's based upon ideas of Pronk and Ferrar. Here I've written this only for no nonlinearity, where you sort of do a lot of integration by parts, and then you can sort of save the mild solution formula like you're used to. Okay, so this I did with Alexandra Nermtu. That's a result that we proved in 2018 that finally got published in 2020. So this was just, I inserted this as a word of warning. If you are in quasi-linear, some of the stuff I'm going to tell you is not as easy to apply as when we are in the case when A will not depend upon U. Like, for example, take the Laplacian. All right. All right, let's get to the results. So let's see how much time I have. That's very nice. So let's get to the real results. Let's focus on this equation, du AU plus f of u plus additive noise. You can stick in a linear operator B in here. This doesn't matter too much. The B you just carry around. It just pre-multiplies effectively the series that defines the W. It acts on the spatial components, so you can just stick a linear operator. And it's like a matrix in finite dimensions that you stick in. So assume that Q is trace class, so it has a well-defined trace, a finite one, and then you can easily, look into the literature and you find that the standard mild solution with the semigroup formulation exists, and it is written in this form that I had on the previous slide, and this is a very nice equation. So now what's the setup when we want to do bifurcation theory for PDEs? let's assume we assume the noise for now, the sigma is sort of sufficiently small, and we are trying to understand the perturbation from the sigma equal to 0 case. And suppose we are starting with homogeneous solutions. And suppose also we have just taken the homogeneous solution, subtracted it, and moved the branch of homogeneous solutions to u star equals 0 for the deterministic PDE, right? So I'm assuming the typical setup of classical Crandall-Rabinowitz type bifurcation theory for PDEs, that there's a homogeneous branch for the deterministic problem. And I assume that, well, there's a nonlinear term, and I also assume that the additive noise is sufficiently small. And I have a parameter in the problem that is sort of hiding somewhere in the nonlinearity or in the linear operator. For example, here I've written it explicitly that I've just put it in the linear operator. And if I shift this P, if I have this formula that I have P times identity plus some other operator curly A, then this just means I'm sort of moving around the spectrum of curly A, right? Because with the P, I can just move around that spectrum. So at some point, I expect that there's a bifurcation for the standard Laplacian with suitable boundary conditions. This is the case. So let's assume that bifurcation point for the deterministic problem upon moving the spectrum in the linear part around occurs at P is equal to 0. Yeah. Again, this is nothing else but standard Crandall-Rabinowitz bifurcation theory for the deterministic system. So the question is, why even bother with the noise, and what can I learn from the noise and the problem when I approach this deterministic sort of bifurcation point? When I vary my P, what does the noise do in the vicinity of that bifurcation point? And it turns actually out that you can use the noise even to show before the bifurcation point occurs that there is destabilization upcoming. So there is a sort of early warning sign for destabilization in noisy systems that you can exploit. So I want to sort of go through this in a little bit of detail, what the noise is doing near this bifurcation point at P is equal to 0, the deterministic bifurcation point. So how can you analyze this by pen and paper? Of course, the proof is long, so I've sort of reduced it down to the key calculations. All right, what are the key calculations? Let's first suppose we take the linearization case and we are purely focusing on the linear part, and you can estimate the nonlinear terms at some point, right? So let's assume f is 0, and let's also assume as t tends to infinity, we are in the sort of stable case, so we are sort of close to the u star equal to 0 branch in the beginning, and we are interested in what happens with the fluctuations near this u star equal to 0 branch, near the homogeneous state. And we are purely interested in this on the linear level, right? If I do this, then this term here drops out because it's exponentially stable, because the semigroup is decaying if I'm below the bifurcation point. So suppose I'm attracting, and suppose this guy here is dying out. I've already supposed that I can somehow estimate the nonlinear terms and everything is hidden in the linear terms. This leaves me just with this stochastic integral that determines the fluctuations and the interaction between the deterministic semigroup S and the stochastic term W, right? Because this encodes everything, right? The nonlinear terms I've estimated, the initial condition has died out. I'm in the locally linearized regime. This S of t minus S is effectively the deterministic semigroup from my linear operator, and the W is the noise, and I have to somehow treat this integral guy because it will give me the fluctuations locally near u star equal to 0. All right? This is the stochastic convolution I have to treat, and the easiest way to treat fluctuations is to look at the moments of the fluctuations. In finite dimensions, this is pretty easy. You look at the variance in one dimension for the second moment, which would be the next natural characterization of the noise and the fluctuations of your stochastic process. In n dimensions, you look at the covariance matrix, right? And in infinite dimensions, you can look at something that's called the covariance operator. This C of t that I've defined here is effectively the fluctuations in infinite dimensions of sort of the second moments of this stochastic process. Yeah? And it's sort of the same definition if you unravel it, like you normally would write the covariance matrix in finite dimensions for a linear process. You will see that this formula reduces in finite dimensions to what you're used to for the normal covariance matrix. Have to trust me on that. But once you have that formula, you can actually prove, and that's an important sort of fact, that if you take the limit, so the long-term fluctuations of the covariance matrix below the bifurcation point, they satisfy a rather funny looking equation. Yeah, so there's a long-term stationary limit of the fluctuations around the U star equal to 0 state that satisfies this funny equation here. Most of you have, of course, spotted already that that's not a funny equation, but you know that very well from finite dimensions, these types of equations. Namely, these are Lyapunov type equations for matrices in finite dimensions that have the structure somehow AC plus CA transpose plus BB transpose equal to 0. Yeah, if you put that in, that's sort of its own area in control theory and finite dimensional matrix analysis. And this is nothing else but an infinite dimensional version projected on basis functions of a Lyapunov equation. Nothing else. Yeah. And let's suppose now we want to study this Lyapunov equation, varying the parameter p, getting closer and closer to the bifurcation point. And we want to understand how the stochastic fluctuations, so how this covariance operator changes when you approach this deterministic bifurcation point. Okay, you can do that actually. And when you study this equation carefully, you will figure out that certain theorems hold. For example, this is a theorem. Suppose you're on a bounded domain. Suppose you have a nice basis. Then you can actually prove that there's an explicit formula how this stationary covariance operator behaves in the regime as you're approaching the first bifurcation point, the typical Crandall-Rabinowitz type bifurcation point from below when you vary p. For example, if you have a Laplacian and suppose you have the right boundary data that the first few eigenvalues are 0, then you see that as p tends to 0, there's actually on the lowest order modes of the eigendirections where the eigenvalues are closest to 0, you see that this sort of covariance operator, when projected onto these basis elements, grows like 1 over p as p approaches the bifurcation point. This just means there's a 1 over p scaling law of the fluctuations of the noise as you are approaching the bifurcation point from below, and these are sort of governed effectively by the sort of weakest stable eigendirections. Yeah? So these govern how you sort of see these fluctuations, and this is just encoded in this formula. Right? All right, even further, you can do this with essential spectrum when you're, for example, on unbounded domains, but you get a weaker result. So this is what we proved with Francesco Romao. I should say the first result is joined with Karna Gauder from 2015. The second is joined with Francesco Romano from 2018. If you have essential spectrum, then you can actually prove that the boundary of the essential spectrum has an approximation by eigenvalues. That's the classical theorem of Reeds. And you use this Reeds theorem to say, all right, I look at the boundary of the spectrum as it approaches the sort of first bifurcation point. Then again, the covariance operator blows up as p tends to 0, but you cannot determine the precise blow-up rate because there's so much information encoded in the essential spectrum becoming unstable. So again, it just says that if you go, now there's a much more sort of broad possibility how the fluctuations could blow up if you have more spectrum that approaches the axis. That makes sense intuitively, right? Because you have simply a lot more directions where the noise could sort of excite your system. So all of this is sort of intuitive, right? There's no non-intuition in these results, yeah? And of course, you might wonder now, suppose you maybe want to make this all dynamic and want to make the bifurcation parameter dynamic. So that's my second challenge that the organizers asked me for. The second challenge would be to make these static results for static or sort of quasi-static parameter or adiabatic parameter variation to make them more dynamic. Meaning to assume that P has its own dynamics and then approach slowly the bifurcation point. And we have a few sort of first steps with Manuel Gnan, and we're also working with Marc Ferrar on this problem at the moment. All right, so let me check how much time I have left. Very good, I still have a little bit of time, I think. So I also want to give you a practical way of calculating these things in your SPDE models. So from the analytical results, I also want to show you a little bit of numerical continuation methods to actually get these scaling laws and the fluctuations numerically, if you ever encounter an SPDE in your modeling. Suppose you did a spatial discretization of your PDE. If you do that, you obtain a big system of stochastic ordinary differential equation because you spatially discretized. You can do the same sort of arguments. Take a deterministic equilibrium, you linearize the equation, you have a varying parameter, you look at bifurcation points, when does the spectrum of this guy go through 0, etc., etc. And indeed, you see that in finite dimensions, the covariance matrix of the linearized process again solves the sort of matrix Lyapunov type or matrix Riccati equation. And in the stationary limit, it solves precisely what we are used to, AC plus CA plus basically BB transpose. I've called this here F because I usually for SODEs, I call this F and big F, but yeah, never mind. Yeah. So, and then you can show, okay, I want to compute these covariance matrices, because effectively what you need to do is to get the scaling law and the fluctuations locally around the branch of stationary solutions, you need to do an effective computation of the covariance matrices, yeah, of these matrices C, because if you had them, you could plot them. How do you plot them? Well, you plot them by defining covariance ellipsoids, which is classically in statistics known as the Mahalanobis distance from the 1930s. And you just stick in a matrix in the inner product and you visualize the fluctuations by drawing an ellipse around your normal branch of equilibria that you see, that you plot normally in your numerical continuation schemes. Right? So you do a normal numerical continuation of your equilibrium, and then in addition, you solve for every parameter value P an algebraic equation. What? This is not so bad, because this we can do a numerical continuation. We are precisely used to this. We are calculating a branch of equilibria varying upon P. For every P, we have to add this algebraic equation that we need to solve. But this algebraic equation is easy to build because the A is the linearization. We have this already in numerical continuation. The linearization, the matrix is already built. You need to add this noise matrix, and you can easily do effective iterative methods to solve for the C. So you can do predictor corrector schemes like you're used to. Yeah, Hannes in the next talk will definitely say a little bit more about numerical continuation. So, but you just add this algebraic equation for the computation of the covariance matrix into your standard predictor corrector scheme for the numerical method of the continuation, and you compute the family of matrices C. All right, let's try to carry this out. So here's the cubic quintic Allen-Kahn equation, yeah, in say 2D, yeah. What we do is we first compute the deterministic bifurcation diagram. Yeah? This can be, for example, done by PDE2 paths, like I have done here. Again, Hannes Lücker in the next talk will tell you more about PDE2 paths, so I don't have to do that here. Then you consider the sort of SPDE version, so you do your modeling, except that now not only the normal Laplace and the normal diffusive modeling takes place, but also the diffusive modeling of the noise part. Yeah. For example, take trace class noise, yeah, and you discretize this whole thing in space. You get this big system of stochastic ordinary differential equations. And for this, you apply the numerical continuation method I've just shown you. You add an additional algebraic Lyapunov equation, and you solve that by a predictor corrector scheme. Well, this can be done, and here's the result. So this is the deterministic bifurcation diagram from PDE2 paths. There's the homogeneous state for the cubic quintic Allen-Kahn. It has bifurcation points, yeah, and it has nice branches, and you can here get a fold, for example, for cubic quintic, and you have another branch, and there are patterns, yeah, you get a bump and a double bump and a rotated double bump effectively, and so on. And let's focus in on this fold point. And let's suppose we are going from the upper branch, this blue branch, which is deterministically stable, we are going down, and we are interested in how do the fluctuations go up as we approach the fold point, right? Suppose we do that calculation, and then we see that the scaling law, as we follow this blue branch, here's the fold point actually, and these little blue lines for different sizes of the noise tell you how the noise goes up for different noise sizes. They sort of these are the covariance neighborhoods. Here I've just plotted a matrix norm of the finite dimensional covariance matrix effectively, and you see that the covariance matrix in its norm sort of blows up as P goes towards the bifurcation point. Of course, this is not a bifurcation point that's a classical Crandall-Rabinowitz type crossing like a transcritical or a pitchfork, but it's a fold. And indeed, the fold has not a scaling law of 1 over P, but 1 over square root of P effectively. And this dashed line is the sort of classical Crandall-Rabinowitz 1 over P scaling, and this thick black line is the 1 over square root of P scaling. And indeed, your numerical method for different noise sizes correctly in the log-log plot recovers the 1 over square root of P scaling of the noise blowing up as you approach the fold point. And you did that basically at the press of a button of the computer, which is very nice. So you can investigate stochastic fluctuations now with automated numerical continuation methods along branches in your favorite SPDE model. Yeah? And it works on a standard desktop. And it's actually also an early warning sign for that bifurcation, because you can monitor how this scaling law behaves, and you can then calculate backwards where is the critical transition point. So where is the P critical? If you know that it blows up like 1 over square root of P minus P critical, then you can recalculate basically from the log plot where the P critical has to be. Yeah. Very good. So let's summarize this a little bit. I hope I'm roughly on time with the planning. We started a few minutes late. I'm supposed to go 25. So I've shown you 2 sets of results. One set of results was about analysis of deterministic systems with a bit of noise and how to capture analytically stochastic fluctuations when you are approaching this deterministic bifurcation point. And you see that you can do this. You know, there's lots more you need to prove, of course, that I haven't put in this talk because it's not really a stochastic sort of background audience. You can show that you have these fluctuations that grow as you approach this point, and then you can actually estimate that that's sort of the leading order behavior up to a certain neighborhood of the bifurcation point. Yeah, but then I've also shown you in the second part more sort of applied view of that you can calculate these neighborhoods and the stochastic fluctuations with numerical continuation algorithms. And we have used this, for example, in the Atlantic meridional overturning circulation to understand how fluctuations in the Gulf Stream actually behave. Yeah, we have also given detailed numerical error estimates for this algorithm. We have implemented it for sort of SODEs, or I've implemented it for SODEs and for SPDEs, and it's really very robust and fast. So if you want more information, please go to my website that sort of tries to be easy to remember somehow by its name. And then lastly, I would like to thank you very much for your attention. And again, thanks to the organizers for inviting.
Thank you, Christian. Thank you very much for your talk. Other questions from the audience?